All right, so Bio20 is before we learn about the next stage of photosynthesis or the light dependent reactions, which is the production of NADPH, okay, or here the production of NADPH. We need to learn about something called a oxidation. Where the heck am I going here? Okay, here we go. Oxidation reduction reaction or redox reaction. So let's get into it. If a substance is oxidized, it loses electrons. Okay? And so we saw those passing of electrons through the electron transport chain earlier. So there was already oxidation reduction happening. Reduction is gain of electrons. Oil, rig. Oxidation is loss. Reduction is gain. Okay, now, so through the electron transport chain, I keep messing this up. Okay, we have electrons passed from photosystem 2 to plastoquinone. Okay, quinone, my bad. Okay, anyway, photosystem 2 loses electrons, so it's oxidized. Okay, and plastoquinone gains electrons, so it's reduced. And then the electrons are passed from plastoquinone to the cytochrome complex. And so plastoquinone is oxidized and the cytochrome complex is reduced. And then the electrons are passed here, right? So oxidized, reduced. And then they're passed here, so then oxidized, reduced, and so on. Okay, so we have lots of oxidation reduction reactions occurring already within the electron transport chain. So in this diagram, all right, we're really focusing on the orange arrow. All right, that is what we're really worried about, where we have a reducing agent that holds the electrons that are passing the electrons to the substance which is reduced. Okay, we have the oxidizing agent which will be reduced. It will get the electrons. Okay, so the reducing agent becomes oxidized after it passes its electrons. The oxidizing agent becomes reduced after it gains the electrons. So in the next step of photosynthesis, NADP plus will be reduced. It will gain 2 electrons to become NADPH. Now, we need a proton or a hydrogen ion, all right, to balance the charges, all right, and to be able to hold, so NADP plus can hold the 2 electrons. Notice that NADP is a 1 plus P is a 1 plus ion, and hydrogen ion is a 1 plus. So we have 2 pluses. Notice that NADPH does not have a charge, so here's the 2 minuses, which balance out the charge. So that's why the hydrogen ion is needed. It's needed to balance out the charge and to hold those electrons. Okay, so NADPH will be created in the light dependent reactions. This reaction here, which I should have put this one on top and this one on bottom, but that's okay. This reaction here will happen in the light independent reactions, and we'll look at it later. So in this set of reactions, we have photosystem 1. Okay, let's just remember where that was. Okay, photosystem 1. Okay, so we have photolysis, the ETC. Okay, photolysis produces the electrons. The electrons are passed through the ETC. The protons are pumped in that process and they accumulate in the thylakoid lumen. They'll be used later here. Okay, Here's where we are right now. The electrons have been passed here. Remember, they've lost all their energy and they're back at a low energy state. All right. So in photosystem 1, light energy again is used to excite the electrons and bring them to a higher energy level. Then they are passed, and we're not going to worry about these enzymes here. Okay, they do this reactions. They are then passed to NADP plus, which incorporates a hydrogen ion here to produce NADPH. So NADPH is actually a high energy molecule because it contains two high energy electrons. Okay, and so it's storing those high energy electrons, which will be used in the light dependent reactions. Okay, so NADP plus accepts two electrons, it's reduced. Okay, and PS1 is oxidized, okay? And then it's converted to NADPH. So light energy excites electrons. Electrons are transferred to NADP plus, which becomes reduced. At the same time, photosystem 1 becomes oxidized. All right, and a hydrogen ion is incorporated. And NADPH, a high energy molecule, is produced out of this reaction. Finally, the next step of reactions will involve ATP, and then we'll do a review here. So I'll do this in this video, and then I'll do the review in the next video. ATP, adenosine triphosphate. Okay, it was considered to be the energy currency of life. It runs all, it's like a little engine that runs all of the chemical reactions within cells. Any energy is needed within cells is done by ATP. Glucose itself is a energy storage molecule. It cannot be used directly for cellular energy. All right, glucose will be used later on, okay, to make a ton of ATP by the mitochondrion. But there's a little bit of ATP made in photosynthesis. So we'll look at the ATP molecule now. Okay, so these are all roles of ATP that you can write down and make sure you understand and know. All right. So in the reaction to make ATP, we have ADP, adenosine diphosphate, plus a phosphate to produce ATP. Okay, so this is the simple reaction. Phosphate is P with the subscript little I. Okay, that means phosphate. So adenosine diphosphate has some energy, but when the last phosphate is added, it's like a full charged battery. It has tons of energy. My biology told me to visualize the bonds between the phosphates as being little springs. Okay, and so when the phosphates are loaded in, it's like a loaded spring ready to release its energy. That's all you need to know there. So where does this occur? Okay, so I've blocked out a few things here because they're not important for the process of chemiosmosis. What's important for the process of chemiosmosis? Well, what are we looking at here? This is the big protein in the middle of the electron transport chain. Okay, so here it is here, all right? The protein in the middle of the electron transport chain is what we're looking at. And then we're looking at this protein called ATP synthase. Okay, so those are the two here. So I blocked everything out so we can focus on what needs to be focused. Now, remember that protons were produced in the photolysis of water, and protons have been pumped into the thylakoid lumen by the ETC. So we have this accumulation of protons which creates a gradient of protons. And it's really important to understand that proton gradients, or any gradients, or any stuffing of anything into a space will be a form of potential energy. Now, ATP synthase will use the energy because what will happen is that these protons will want to diffuse back to the stroma to go into equilibrium, equal concentrations on both sides of the thylakoid membrane. But they can't. They're protons. They will try best they can, but they will be repelled by the phospholipid bilayer because any ions cannot pass directly through the phospholipid bilayer. They will repel any ion. So an ion needs a channel to go through, all right, to what's it called? To move back, to diffuse there into the stroma. Now, the energy of this is like a dam, okay? Imagine a hydroelectric dam. It's damming protons, okay? And those protons are going to want to go through the dam. Now, this ATP synthase is like a turbine, all right? And so in a hydroelectric dam, the water is held back and then it's released. Okay, the potential energy of water is released through turbines to create electricity. In this situation, protons are released through ATP synthase, and ATP synthase is going to produce ATP. It's going to run the reaction, that will fully charge the battery. This reaction here, ADP plus phosphate to produce ATP in the ADP synthase. There's a little animation here. It's pretty good. I'm not sure if it'll be confusing because it uses a little bit of a different visualization for things, but watch it, see what you get out of it. Okay, thanks a lot. And I'll do one more lesson to review all of the steps and processes of photosynthesis right away here.